Hello, good afternoon, good morning, and welcome to IEA Bioenergy webinar series. My name is Chiara Benetti, and I welcome you on behalf of ETA Florence Renewable Energies, technical organizer of this webinar. Today's webinar is entitled Scaling Up Advanced Biofuels Production and is moderated by Tina Bakovsky, Scientific Advisor Biofuels at BEST Bioenergy and Sustainable Technologies and Chair of IEA Bioenergy TCP. The speakers will be Andrea Sonnleitner, Senior Researcher at BEST Bioenergy and Sustainable Technologies, and IEA Bioenergy Task 39 National Leader and partner of the BioTheRoS Project. Then we will have Dimitrios Korokompas, Senior Research Engineer at the Center for Research and Technology, HELLAS, and coordinator of the BioTheRoS Project. Patrick Royerman, Senior Consultant at BTG Biomass Technology Group, and also partner of the BioTheRoS Project. And Teresa Köfler, Junior Researcher at BEST Bioenergy and Sustainable Technologies and partner of BioTheRoS Project. As usual, you have the possibility to drop questions during the webinar by using the Q&A tab that you can find at the bottom of the screen. Our speakers will reply to your questions either by answering to the question by typing the answer in the Q&A tab or by answering live at the end of all presentations during the Q&A session. Please do drop the question in the Q&A tab and not in the chat, which is supposed to be used just for greetings. The presentations and the registration of today's webinar will be available on IEA Bioenergy website from tomorrow on, as usual. And that's all from my side. So I'll give the floor to Dina and enjoy the webinar. Thank you.
Thank you very much, Chiara, for the introduction and the housekeeping in here. So a very warm welcome to all of you in any place of the world that you are listening to us today. Thank you for joining this webinar on scaling up advanced biofuels production. This is a webinar organized by IEA Bioenergy Task 39, which is on commercializing biofuels in partnership together with the EU project on BioTheRoS. So why are we doing this webinar today? Because globally we need to get to net zero greenhouse gas emissions by 2050, which means we need to decarbonize all sectors, including the transport sector, which is particularly difficult to decarbonize. But biofuels are a very good tool in decarbonizing the transport sector, not the only one, but a good one. Somehow limited probably by feedstock if we don't manage to unlock the potential of advanced biofuels, technologies that are able to produce biofuels also from lignocellulosic feedstocks and more difficult feedstocks. So where are we in terms of these technologies that are a bit more difficult in their development and their deployment? So we will have two presentations helping us understand where we are. One from Andrea Sonnleitner and the Task 39 perspective, and one from Dimitris Koukoumpas with the BioTheRoS project view. And after that, we will go into more detail on the pyrolysis and the gasification technologies. So with this, I would like to turn to our first speaker, which is Andrea Sonnleitner, Senior Researcher at BEST Bioenergy and Sustainable Technologies, and the Austrian representative in IEA Bioenergy Task 39. Andrea, please provide your presentation.
Thank you very much, Dina, for the introduction. You will see my presentation now, I hope so. Yeah, what is the aim of my talk today? So I want to give you some insights of the assessment of demonstration plants and commercialization progress we did within the IEA Bioenergy Task 39 network. And therefore, I will introduce our task. What is IEA Bioenergy Task 39? The scope of our network is the biofuels to decarbonize transport. And we have in task 39, 16 participants and member countries. And as you can see here on the screen, we are divided on the different time zones and the different continents. So member countries are ranging from Canada, United States, Brazil. Then a lot of European countries are joining this task. We have South Korea, Japan, China, and New Zealand. And what are we looking at in the task 39? So we try to analyze policies, technologies, markets, and sustainable biofuel implementation. And here you have listed the different projects or topics we're dealing with that are sustainable aviation fuels or biojet, drop-in fuels, implementation agendas, marine fuels, demonstration facilities, certification, biofuel policies, sustainability, the commercialization progress, also synergies with green hydrogen, and biofuels in emerging countries. And within our network, we're trying to do cooperations with other IEA Bioenergy TCPs or IEA TCPs, and also with projects like, for example, the BioTheRoS Project, where Dimitris Koukoupas will tell you more after my presentation. At this point, I will also like to invite you to have a look on the Task 39 webpage, where the recently published reports of the task are available. So there are reports on sustainable aviation fuels, on drop-in fuels and co-processing, on biofuels in emerging markets, and also the implementation agendas report on biofuel policies. So what technologies are we looking at in our task? So there are many ways to produce liquid and gaseous biofuels from biomass, either from crops or from dedicated crops or from residues and wastes. And here you have a graph from IEA Bioenergy where you can see the different technology pathways and also where they are at the technology readiness. So commercial applications are ethanol from sugar and starch crops, biodiesel and hydrotreated vegetable oil, also biogas and biomethane from anaerobic digestion. Biomethane from gasification is already in an early commercial phase. And then we have some technologies which are in the demonstration phase, like cellulosic ethanol production, Fischer-Tropsch liquids, pyrolysis-based fuels, and hydrothermal liquefaction-based fuels. And we in the task 39 are mainly focusing on advanced biofuels, and there we assess and track the development of advanced biofuels demonstration facilities. So we have this database on facilities for the production of advanced liquid and gaseous biofuels for transport. And we are tracking this development since 2009. So we have seen a lot of developments in the recent years. And you have here within this database and map the possibility to search and filter for different facilities and technologies. So we have here listed alcohol to jet as technology, e-fuel biomass hybrids, fast pyrolysis, fermentation, gasification, hydrothermal liquefaction, hydrotreatment, lignin depolymerization, and others. And there is also the possibility to filter on the status of the facility. So is it a planned or announced facility? Is it already under construction or even operational? And you can also filter raw materials or the output of the facility. And from this database and the entries we have there in the database, I want to show you two examples of such demonstration facilities. And those are from thermochemical technology routes. And afterwards, Patrick Reumermann will tell you more about the pyrolysis technology, and Theresa Köfler will tell you more about the gasification. So one of the examples I brought with me is the Pyrocell plant in Sweden. This facility uses the BTG-BTL pyrolysis technology, and the upgrading is then done in an existing refinery. The other example is the syngas platform in Vienna, which is a biomass gasification plant with a Fischer-Tropsch synthesis. But as I said, my colleagues will tell you more afterwards. Now I want to give you some insights on recent developments we have seen within assessing the demonstration plants and the commercialization progress. So the main technologies listed in our database are fermentation, gasification, hydrotreatment, and fast pyrolysis, whereas the hydrotreatment is already commercial available. We've seen in the last years a rising number of facilities and also a rising number of planned facilities. There were many announcements in recent years, also for the production of sustainable aviation fuels. Then we also see a diversification of technologies and the combination of different technologies. Like, as I said before, we have some listed which are e-fuel biomass hybrid systems. There are also more and more co-processing facilities, and we see an increase in retrofitting oil refineries. We saw also that more and more waste streams are used, and also waste streams from non-biological origin, or the recycled carbon fuels, like, for example, flue gases as feedstock for gasification. And with our global view, we also saw the increasing development in emerging countries and in Asia. But what we also see is that commercialization takes time. There is a slow progress for some technologies and also many setbacks in commercialization process. So there are cancelled projects or announcements which are not leading to facilities. As I said, there is now a focus on sustainable aviation fuels production. So there are many plants with SAF capacity or planned SAF capacity, and many announcements for facilities producing sustainable aviation fuels. And in the existing facilities, the SAF fraction can be increased. So at the moment, the main technology is the hydrotreatment technology, and their SAF is only one of the possible products. And the fraction which is produced the most is depending on economics and policies. But there is potential that in those facilities, the SAF fraction can be increased. And as I said, main technologies is hydrotreatment and co-processing, but it's also possible to have alcohol to jet or power to liquid or gasification. And here are some examples of companies. like World Energy, Neste, Eni, or BP. But why is it so important to demonstrate technologies and to scale up the facilities? So the demonstration validates the feasibility and the efficiency. So within the real world settings, the effectiveness can be confirmed, and it also crucial performance data can be provided. It's also important to have a variety of feedstock. So the demonstration of the different technologies is of importance. To use different feedstocks and waste streams, and to also see in real world setting how the feedstock supply chain can work. The scale up reduces production costs through the economies of scale. And we see that reaching commercialization is critical, but we also see that it takes time from the announcement of a plant facility up to the operation. And there is the risk of scaling up too fast, and which can lead to failures and to setbacks for the technology. And there are also challenges for demonstration and scale up, which I give you on the next slide. So here are listed implementation barriers for the production of advanced biofuels. This is economic implementation barriers, like the high production costs of advanced biofuels, the financial risks of demonstration, and first of its kind facilities. Then we have uncertainty of regulatory framework and policies. Another important barrier is the availability of feedstock and the sustainability of feedstock. And in some countries, the policy is focusing on other options than liquid biofuels. But we also see a lot of opportunities for liquid biofuels. So the technologies are based on broad variety of biomass feedstocks, which leads to diversification of energy supply. Biomass production provides regional income, and we can use biofuels in current vehicles and the existing infrastructure, so we have immediate greenhouse gas emission reductions. And the high energy density of liquid biofuels is an important alternative solution for the hard to electrify sectors in transport. So instead of using liquid biofuels in passenger cars, it's a good opportunity for trucks, ships, and planes. Now, to sum up the insights from our demonstration project in Task 39, we see that we need to drive commercialization forward, and therefore there's the need of demonstration and scale up of different technologies. We need to reduce the costs and financial risks for investors. And it's important to have long-term policies and comprehensive strategies. We see positive development in particular in emerging countries, and we see the promising opportunity of long-distance transport. And the variety of different technologies and new demonstration facilities is a big advantage for biofuels and the transport sector. And more information on this topic will be available in the publication, in a report on this project. I think it will be finished within this year, but it will be published then in 2025. So that were the insights from Task 39. Thank you very much for your attention. And if you have questions, please state it in the Q&A section. Thank you very much.
Thank you very much, Andrea, for this first overview on where do we stand in terms of advanced biofuels demonstration and deployment. I could already see some questions dropping in. I already picked one that will be answered live in the discussion, but we will keep all questions until we've heard all presentations. And also those people who post questions in the chat, please repost them in the Q&A part, not in the chat. Otherwise, we will not be able to see them properly and address them. So with this, we go to the next presentation. I would like to invite Dimitris Kourkoumpas for his presentation. He is Senior Research Engineer at the Center for Research and Technology Hellas, like CERT, and he is the coordinator of the BioTheRoS Project. And I understand that this is a project to help commercialize thermochemical technologies and bring forward the development of these technologies. So Dimitris, the floor is yours.
Thank you very much, Dina. Please let me share my screen. Okay, I hope that you can see my screen. So, as Dina mentioned, this one is a Horizon European project regarding the scale-up of the activities, especially for the thermochemical routes. So it's a project funded by the European Horizon Program under the grant agreement and running from 2023. So we are on the first year of the project. The project consists of 6 partners with very dedicated roles. Please let me describe in brief the role of each partner. CERT is a research institute in Greece, and we coordinate this project. And regarding the technical part, we operate a carbon capture unit, and we are responsible for the modeling of the investigative value chains that we will see in the later slides, in the next slides, through different models like CFD, process modeling, and life cycle analysis modeling. BDG is the partner for the lead for the pyrolysis pathway. BEST is the leader for the gasification pathway and for the networking activities. CIRSE is responsible for the logistics, for the biomass logistics. Motor Oil, the refinery, is the end user, the industrial end user, while WIP is responsible for the dissemination activities. So in this project, we investigate 2 demo cases. One for the pyrolysis and upgrading units in Netherlands, and the next one, the other one, is the gasification unit in Austria. Okay, so regarding the objectives of the project, first of all, the scope, the first objective of this project is to develop a cost-effective and sustainable technologies for thermochemical conversion of biomass to produce biofuels to TRL5. The second one is about for the identification of the biomass feedstocks, so to provide specific models regarding the selection, the assessment of biomass, and the prediction of a biomass demand through AI models. In this project, as I mentioned before, we are going to demonstrate specific technologies, pyrolysis and gasification. So we'll develop scale-up rules, because the issue here is how we can go from the TRL5 to TRL9, so to go to large-scale applications. Of course, we have to identify concrete measures for improving the sustainability of those technologies. And finally, to provide valuable insights into the market dynamics, since we have to investigate the market penetration and how these technologies can be penetrated in the market. Some breakthroughs that we investigate in this are elaborated in this project. First of all, regarding the value chain, we investigate the full value chain, starting from the logistics of the biomass until the end use, the production of high quality product, and the end use industrial, let's say, state. We investigate innovative units for carbon capture from the gases from pyrolysis and from syngas. So we integrate this technology, the carbon capture technology, in order to improve the efficiency of those technologies. We utilize RES, hydrogen, green hydrogen, in our pathways. We develop a very specific and very innovative framework regarding the life cycle analysis, life cycle costing, combining all of them, also with social terms under a multi-criteria framework in order to provide to the users, to the stakeholders, the most valuable pathway in sustainability terms. And finally, we develop those holistic guidelines for scale up and for those technologies. Please let me describe in brief, since my colleagues later, Patrick from BDG and Teresa from BEST will describe in more detail their facilities that are involved in BioTheRoS Project. So just a brief description here. BDG operates a lab, a pyrolysis bench scale unit with capacity from 2 to 5 kilos per hour, and a larger scale pilot plant from 80 to 200 kilos per hour. In this project, in BioTheRoS Project, we will investigate through this pathway 2 feedstocks, forestry residues and wireless raw. So as you can see also in the figure, starting from those biomass and through fast pyrolysis, we produce fast pyrolysis bio-oil, and then by upgrading through hydrogeneration, we produce HPO that is fractionated into naphtha, SAF, and the renewable marine diesel. This one is the first pathway. The second one pathway is under the supervision of BEST colleagues. So here BEST operates a plant about 1 megawatt scale of a reactor with capacity 200 kilos per hour. It's and 250 kilowatt pilot Fischer Tropsch synthesis unit. So starting from the wood chips, this one is the feedstock that we use in this pathway. And forestry residues. Forestry residues is the feedstock for BioTheRoS Project, which is, let's say, the baseline pathway, and following the specific pathway for producing syngas and then through Fischer Tropsch to produce SAF. This one is the second pathway of BioTheRoS Project. Which is now our methodology, which are the activities that how we address these technologies and what we do in BioTheRoS Project. First of all, we investigate the biomass supply, so the biomass potential, the whole logistics about the treatment that maybe is required. Then we do lab scale activities first, and then the pilot scale activities in the facilities that I described before, in order to produce a plethora, a number of final biofuels to be used either in aviation sector or in maritime sector. For these activities, of course, we support and we do modeling regarding, for example, process modeling in order to evaluate the scale-up scenarios, so to identify the most critical parameters and to try to optimize this one of the scale-up scenarios. We do, of course, experiments, LCA analysis for the environmental assessment of all these activities, and finally, the analysis regarding market dynamics and business modeling in order to find opportunities in the market for those fuels. Of course, we are in contact with stakeholders and collaboration with other projects in order to be in line and to synchronize our activities. Just about now the new value chains that are designed within BioTheRoS. We identified non-food feed biomass resources with the highest replication potential for aviation and maritime biofuels production. So this one is about the biomass potential assessment. Then we select biomass pretreatment technologies. So we investigate which are the pretreatment technologies that is the most appropriate for those biomass, of course, in terms of cost and technical, of course, requirements. Then we identify the type and the role of each stakeholder in the whole value chain for the scale up. And finally, we develop predictive demand models in order to know exactly which is the biomass needed for the industries. Just here, the validation about the products and evaluation. For the pyrolysis, we start from the operation of a multi-step hydrotreatment process to produce HPO. We identify the constraints and opportunities for scale-up pyrolysis pathway. We operate the whole value chain, including the distillation units to produce light jet fuels and the road marine fuels. We simulated modeling for scale-up of pyrolysis value chain. And of course, we do all the experimental assessment of fuel synergies between pyrolysis fractions and FT fuels. Regarding gasification technology, here again we characterize of gas impurity. We're starting from the characterization of gas impurities and possible catalyst poison and adaptation of gas cleaning section. We identify again here the constraints and opportunities for scale up, operate the fuel process in order to obtain the FT-RO product, to upgrade this one into high quality sustainable biofuel, and finally modeling simulation of the assessment of the possible scale-up technology. This one is the framework, the description about the life cycle analysis. So we will develop a specific framework for the whole value chain under life cycle thinking using ISO standards. The same work for the life cycle costing, the life cycle thinking in terms of cost, and for the social analysis, the same in the social dimension. So we'll combine all of these pillars under one using multi-criteria analysis in order to present the most sustainable pathway for the stakeholders. Of course, we will do also techno-economic assessment of CCUs and the renewable hydrogen as add-in options to advance biofuel pathways. The impacts regarding from the BioTheRoS project, of course, is first of all to optimize the process from biomass to biofuel. So we see which are the points that needs to be improved in this value chains in order to go for the scale up. Of course, based on the work that we are going to do, we build knowledge for upscaling, the biofuels efficiency enhancement, so to overcome technical bottlenecks, and of course integration of CCU and the renewable hydrogen will improve this the efficiency of those technologies. Of course, the best available alternative will be identified through the multi-criteria analysis, so to identify the best available scenarios. The economic viability is another impact that we are going also to have during at the end of this project. So to provide a techno-economic analysis in order to evaluate the economic performance of those technologies, and of course, as I mentioned also in the beginning, let's also not only with technology providers, not only with other, let's say, partners that are working on that, but also with international networks and other projects. Synergies that we have, it's of course with government and the regulatory bodies and the research stakeholders in order to provide this guideline that we are going to develop. Of course, with the fuel producers and suppliers and airlines and shipping companies. So as you can see, we are looking for synergies with all stakeholders in the whole value chain. And of course, very critical is also the biomass providers, because biomass potential is, let's say, the first aspect that we investigate and we have to take into consideration. And of course, the social acceptance of our work is always an issue, and we like also to have synergies also with and to provide our own to the citizen. Some take-home messages. First of all, the sustainable supply of quality, cost-effective feedstocks to future biorefineries is fundamental to growing the bioenergy industry. The managing biomass supply chain risk is a critical part to favor long-term sustainability of advanced biofuels in terms of adequate fuel supply. The deployment of a holistic circular economy driven guidelines for the full supply chain of advanced biofuels is needed, both for aviation and maritime market. So constraints and opportunities for scale up will be highlighted and will be also provided through the project. Project will provide mitigation plan about those for the constraints. And finally, the increasing focus on the greenhouse gas impact of maritime and aviation biofuels requires the utilization of life cycle analysis models. So in this context, we develop this life cycle models, this one life cycle analysis framework, in order to investigate the impact of economic, environmental, and social aspect in the integrated way. That's all from my side. Thank you very much for your attention, and happy also to reply to your questions in the chat box. Thank you very much.
Thank you very much, Dimitris. Very comprehensive presentation of the project, which really covers a lot. And I see some very detailed and also some more general questions in the chat. So I like not the chat, the Q&A. And we will come back to some of them at the end of the presentation, and the others you can try to answer in the meanwhile in writing. So with this, we turn to the first technology in the BioTheRoS project, and I invite Patrick Reimerman, who is Senior Consultant at BTG Biomass Technology Group, to present what he's doing in the frame of the BioTheRoS project in terms of producing or work on production of pyrolysis oil and upgrading of pyrolysis oil. Patrick, the floor is yours.
Thank you very much, Dina, for your kind introduction. Allow me to share my screen. My name is Patrick Reumerman. I work for BTG. BTG is an SME located in the Netherlands, and we focus on biomass for energy applications and for bio-based applications. My presentation is about the production of sustainable transport biofuels via pyrolysis upgrading. So in that title, we already have two technologies, which I both will discuss. The first technology, the pyrolysis technology, is about making an intermediate product, the pyrolysis oil. It is a technology where we use biomass particles, relatively small particles, which we heat up in the absence of oxygen to around 500 degrees, and we do that fast. So it is fast pyrolysis. In a few seconds, we evaporate the biomass, and it gets separated into three products. First, our main thing, the organic vapors, then the char, and the permanent gases. The organic vapors we can condense subsequently, and we get our main product, which is the pyrolysis oil. The char and the permanent gases, these are combusted in a separate combustor, which provides energy for the process and drying energy for when the biomass is not dry enough, because we need a quite low moisture content to start this process. The process is efficient and sustainable. The efficiency is quite high if you can have a use of all the heat, and about 60-65% on a mass base gets of the biomass gets transformed into the pyrolysis oil. It is sustainable. It uses non-food biomass, and mostly woody biomass so far, but there is no principal problem with using non-woody biomass. In fact, in the BioTheRoS project, we have one of our two biomass types is a barley wheat, which is a grass-like material. It's a proven technology. There are already 24,000 tons per year plants implemented, one in the Netherlands, one in Finland, and one in Sweden. You saw the one in Sweden at the presentation of Mrs. Zonleiter. And about 100,000 tons of pyrolysis oil has been produced, mostly for the production of heat by replacing natural gas. To use it as an advanced transport fuel, you have to upgrade it. This upgrading, the value chain which we see for that is that we have decentralized fast pyrolysis plants, which are located close to the biomass. And this is because transporting biomass is expensive, since it is bulky, and sometimes the moisture content is also a bit higher, which means that you are transporting for a big part of water and air. So close to the biomass, we have one or more pyrolysis plants. They take in around 40,000 tons dry biomass on a dry basis. And several of those feed into a centralized upgrading unit. This upgrading unit takes in the pyrolysis oil. We use it actually as our term is for it fast pyrolysis bio oil, or FPBO. And then we upgrade it towards HPO, hydro-treated pyrolysis oil. We expect that the minimum size for this centralized upgrading would be around 3 pyrolysis plants, so 70,000 tons per year as input. And the typical size would be about 10 pyrolysis plants, so 240,000 tons per year of pyrolysis oil. Good. Well then, now we have the second technology, the upgrading. And to give an idea about what is there the issue, what is the challenge, we have here a comparison of the fast pyrolysis bio-oil to the left and the drop-in biofuels to the right. If you look at the picture, you already see it. This is opaque, the pyrolysis oil. The viscosity is a bit higher than, for example, here, where you have the aviation fuel. There it is nicely transparent, low viscosity, and the distillate marine fuel also low viscosity and also transparent. It becomes even more apparent the difference when you look at the properties. Fast pyrolysis bio-oil is actually can be described as a liquid biomass. And there is still water in it. 1/5 to 1/4 of the mass is water. In drop-in biofuels, we have hardly any water. The density is 1.2 kilogram per liter. That's below 1 for the aviation fuel and for the marine fuel. A big difference is the heating value. This is 16 for the fast pyrolysis bio-oil, which is comparable to biomass. And it's about 42, 43 for a megajoule per kilogram for these drop-in biofuels. Then there's also one important difference which we very much monitor during our upgrading process. This is the carbon residue if you try to distill the fast pyrolysis oil. A carbon residue of around 15% means actually in practice that you can't distill it. So that makes it very difficult to use it in typical petrochemical processes. Of course, in the drop-in biofuels, you don't have this problem. The carbon residue is very low or low in the case of the marine biofuels. The drop-in biofuels consist mainly of hydrocarbons. And in the fast pyrolysis oil, we have acids, we have phenolic components, some carbohydrates, some ketones. So it is a mishmash of a lot of strange molecules floating around in this soup. Well, how do we change that? Because we have to if we want to make advanced biofuels. We upgrade this biofuel in 2 steps. First, we stabilize the fast pyrolysis oil. We do that with a dedicated Picula catalyst. That's a proprietary catalyst. We use quite high pressures for these types of processes, reasonably medium temperature ranges, and we can stabilize this oil so that it becomes less reactive, and we get a new product, stabilized pyrolysis oil. This is again, this is a liquid which is far more similar to petrochemical products. So it can be used, for example, as co-feeding in a fluid catalytic cracker of a refinery, or it can be used to produce chemicals directly. But we want the transport fuels, so we do a second step. We hydrotreat this SPO. For that, then we can use a standard catalyst, NEMO, COMO, so nickel, molybdenum, cobalt, molybdenum. And for these types of processes, normal pressures and temperature ranges. And we get our product, the hydrotreated pyrolysis oil. This is kind of a more generic transport, a name for a generic transport fuel. If you take this approach and you transform that into how a process would look like, we get this picture. There, this 2-step process is divided into 3 steps. In the first step, and of course you see that this is a fixed bed, we use our Picula catalyst to stabilize the pyrolysis oil. We get as the product the SPO, the stabilized fast pyrolysis oil. After that, we remove the oxygen in the form of water. We do that with a hydrotreatment catalyst, and we get an intermediate product which is stabilized deoxygenated pyrolysis oil, which then needs to be hydrogenated, so hydrogen needs to be added so that we get our hydrocarbons, the hydrotreated pyrolysis oil. This pyrolysis oil can then be distilled via a typical simple distillation process, and we get 3 products. The first, the lights, those are the HPO naphtha fraction. It's around 10 to 20%. Then in the medium range, C8 to C18, we have the jet fuel range. That's about 45 to 55% of the HPO. And then we have, of course, a heavier fraction. We call that the HPO marine fraction. All these three steps need renewable hydrogen, one a bit more than the others, but all needed. And all these steps produce as a byproduct water, which needs to be processed to get an efficient process. Well, how does that look in practice? Well, actually a bit like you would expect. Here we have some laboratory examples of what we did in our laboratory, in our bench scale and our pilot units. We have done this with several types of biomass, with both hardwoods and softwoods. Here you see on the left the fast pyrolysis bio-oil. It is viscous, it is opaque. The SPO is still opaque, by the way, but it looks a little bit better. And then you see HPO, which can be converted, distilled into naphtha, the biojet, and the biodiesel. Of course, these are fully transparent. This one is a little bit less transparent. This is how it looks. Another way to see how it looks is, I'm sorry, it is a big table, but I'll walk you through it. These show the fuel properties of the various intermediate and final products of the upgrading process. And we see here the column, the fast pyrolysis bio-oil. At the end, we see the column of the hydrotreated pyrolysis oil. And what you see is, well, quite encouraging. Our water content from about 1/5 to 1/4 of the mass has decreased to almost nothing. Our density has decreased to around 0.85. Our viscosity has decreased, which is quite nice. And very important, our carbon residue is reduced to almost nothing. Well, how does that happen? One of the ways to look at it is via the elemental balance. And we see that the oxygen is here reduced from about 50%, which is very typical of normal biomass, to almost nothing. And also on the ratios, the H/C ratio, here it is 1.3, 1.5, and with the HPO it is very near to the typical petrochemical range. And for the oxygen over carbon balance ratio, we see that from this it is gone to almost nothing. So this HPO looks quite a bit like these transport fuels. And when we distill it, that's the second table, again, you will see very much what you would expect. We have here the lights, the HPO naphtha, that's the first column. The last column is the HPO marine, and of course the middle column is the HPO jet. There was one question already in the chat about how flexible we are with these products. Well, they are the result of a distillation process. So if you change the temperature range there, you are, in a sense, relatively flexible. In practice, you will be not, because especially the HPO jet is quite a strict specification. The density of the naphtha is a bit lower, and it gets higher if you go to the heavier components. You see the same with the viscosity, very high, a bit higher with the marine and lower with the lighter components. All have a very nice net heat of combustion, about 42 to 44, which is very nice. And the most important point, of course, is the flash point. That for the naphtha, it's very low. For the jet, it is in a fairly low range, and for the marine it's higher. So, in summary, we can upgrade the fast pyrolysis bio-oil to hydrotreated pyrolysis oil, and we can fractionate that into naphtha, biojet or sustainable aviation fuel, and renewable marine diesel. And in the BioTheRoS project, we want to demonstrate the value chain using forestry residues, and as I mentioned, the barley straw, also a lignocellulosic feedstock, as one of the two of the feedstocks for the pyrolysis upgrading process. Here you see again the projects, the three products with their specific fractions when you distill the HBO. We are very happy that we can work in this project. We thank all our partners, and we are happy for that. And I would like to thank you all for your attention. And of course, please put all your questions in the chat, and I will be very happy to answer them. Thank you.
Thank you very much, Patrick. And you have probably not seen yet because you were busy presenting, but your work is just starting right now. There is a lot of detailed questions in the chat waiting for you.
I will do my best. Thank you very much.
Thank you. So with this, we turn to our last speaker, which is Theresa Köffler, Junior Researcher at BEST, Bioenergy and Sustainable Technologies. And she will talk about their part in the project, in the BioTheRoS project, which is the gasification of residues and the synthesis of fuels and chemicals. And Theresa, the floor is yours. So we can well see your slides now in the right
Okay,
mode.
yes. So
Perfect.
I was just struggling a little bit with the presentation. Okay, perfect. So, okay. Also a very warm welcome from my side. My name is Theresa. I will now present you the gasification of residues and synthesis of fuels and chemicals that we are doing at the research facility in Vienna. So I'd like to give you a short overview about the agenda that is awaiting you in my talk in the next couple of minutes. So first, I'd like to give you an overview about the company where I'm working at. Afterwards, I'd like to give you some insights into our plants and research facilities that we have. And afterwards, I'd like to give you some insights into our project contributions in the BioTheRoS project. So, first, I'd like to start with the company where I'm working at. So, BEST is a research facility where we aim on developing innovative solutions in bioenergy and sustainable technologies. We combine, therefore, applied research with industrial collaborations. And I'm currently working at the sub-area 1.3, the syngas platform technologies, and we are situated in Vienna. We have also our headquarters in Graz, which is in Styria, in Austria. Yes. So now I would like to show you this picture of our gasification unit. It's a dual fluidized bed gasification unit, and we call this research site Syngas Platform Vienna, where we have the waste-to-value process chain. So here we combine the 1 megawatt DFB, so dual fluidized bed gasification plant, and the 250 kilowatt Fischer-Tropsch synthesis demonstration plant. Here you can see the picture of our industrial, of our site in Vienna. We are situated at the industrial site of BioEnergy, which is an incineration incineration company. And we have here the DFB gasification demonstration unit. Then we have also in the building adjacent to it, in the middle part in this green tall building, we have the Fischer-Tropsch pilot unit. And then we need also the feedstock containers because for the DFB gasification, obviously, we need some feedstock. And these are situated in the middle part of this picture. And in order to analyze all our products and gases during operation on site, we also have an analytics lab. Furthermore, we are also investigating different novel technologies to optimize our process. For example, we want to investigate new gas cleaning technologies like the temperature swing adsorption. Therefore, we have small-scale laboratory units where we do different experiments and research. Another one of these small-scale facilities is the aqueous phase reforming unit, as well as a small-scale Fischer-Tropsch Fischer-Tropsch laboratory unit. Now I would like to give you an overview about our process. So we are starting with the solid feedstock. In our case, these are residues like from forestry residues or also agricultural residues. But we also have the possibility to use, for example, more difficult feedstocks like sewage sludge. Then we feed all these feedstocks, solid feedstocks, to our dual fluidized bed gasification unit. And there the solid feedstock is converted to a gaseous product, which mainly consists out of carbon monoxide, hydrogen, methane, and also carbon dioxide. To further use this syngas, we need to clean it before we can use it in downstream synthesis. Therefore, a variety of different gas cleaning steps is necessary to get rid of all the impurities and also catalyst poisons. Then we apply the synthesis. In our case, we use the Fischer-Tropsch synthesis to produce transportation fuels and also base chemicals. It is also possible to couple this process with renewable energy sources that provide via different processes additional hydrogen. So here we can also use this energy. Now I would like to get into more detail in our technologies. First of all, I'd like to start off with the dual fluidized bed gasification, which is the first step in our process chain. We have the 1 megawatt demonstration scale plant, which is equipped for long-term campaigns of multiple weeks in continuous operation. The reactor that we use, you can see on the right side of my presentation here. Here. It is an advanced dual fluidized bed gasification. Advanced because we have the second generation of these dual fluidized bed reactors in Vienna, which is based on the 100 kilowatt DFB plant that the TU Wien has invented, basically. And the typical syngas composition is depicted on the bottom part of this slide. So we have around 40% hydrogen, 24% carbon monoxide, and around 20 to 23% carbon dioxide, as well as around 10 to 12, 13% of methane. Now I'm going to the next steps. So to the synthesis of the now cleaned syngas. This is my research area where I'm doing my PhD at the moment. So the Fischer-Tropsch synthesis. We are using a slurry bubble column reactor since it provides enhanced mass and transfer properties, because we have in this reactor that is depicted on the right side, which is a funny drawing. This should show you that we have a three-phase reaction. So this yellow background is the wax that we already provide to the reactor, which is also already the product. But to start the process and to operate the process, we need this wax already in there. So we call that starter wax. And at the process conditions, this wax is in a liquid state. And the catalyst particles, in our case, it's a commercial cobalt-based catalyst, is suspended in this liquid. And then from the bottom, the syngas enters the reactor and the reaction takes place and longer chain hydrocarbons are produced. So the typical product composition or syncrude composition is depicted in this diagram at the middle part of the presentation slide. Here you can see that different products are being produced, different alkanes, also some oxygenates and olefins, and different long chain hydrocarbons can be produced with this process. So now I'd like to give you some insights into our part in the BioTheRoS project. So our gasification value chain looks like that we provide the feedstock to the 1 megawatt DFB gasifier, where we gasify the biogenic waste feedstock, or in general, I would say feedstock. And after that, we have to clean it in 2 steps, like in the coarse gas cleaning and the fine gas cleaning section, where we also look on the gas impurities and develop some new gas cleaning strategies to optimize this process step. After that, like in general, we want to show that we are able to operate the full process chain, and we are able to produce the Fischer-Tropsch raw product that we say we do. And then we give the Fischer-Tropsch raw product to our project partner ZERT, where they hydro-treat it and hydro-crack the raw product to obtain the final sustainable aviation fuels. And they also use it for some simulations and modeling of the whole scale-up of the gasification process. A gasification value chain now looks like that. Here on the left side, you see our feedstock. These are the wood chips. These are the pretty much easy feedstocks, since they are more really homogeneous in their composition. But we also have some quite difficult feedstocks like the forestry residues. But we have also already used sewage sludge, and as you can imagine, like the composition is not really the same if you look at the whole batch that you get. So then we give all these feedstocks, we feed it to the gasifier. And then after the fine gas cleaning, we were able to produce the Fischer-Tropsch raw product that you can see on the right side of my slide. Here we have the wax fraction, and here we have the liquid Fischer-Tropsch fraction. So we were able to demonstrate the full chain operation of this process. To sum it up, our aim is to investigate the biogenic waste feedstocks for the gasification value chain to produce advanced biofuels and chemicals. We are working on using different feedstocks for this process, so that we not only use like this really nice wood chips, but like more difficult feedstocks, which will be important in the future. And we were able to produce the Fischer-Tropsch raw product via the Fischer-Tropsch synthesis. But still, there are some huge scale-up challenges that we face. So, for example, if we look at the gasification unit, as I've already mentioned, we use different kind of feedstocks. So also the syngas that we produce out of these different feedstocks varies a lot. So it can be quite challenging to use different feedstocks in one single gasification unit. Then we have applied the countercurrent column in the gasification reactor part. And this column, or this application enables us that we have lower higher tar conversions, which results in a cleaner syngas. But these countercurrent columns, they are quite complex in engineering. So that's a scale-up challenge that we face there. And our gas cleaning unit has a lot of different reactor types and different scrubber units, and they are quite they have a huge impact on the overall cost of the process. So we are looking on develop novel technologies to clean gas. And if we look at the synthesis part, it is a little bit challenging to scale up the slurry reactor for biogenic syngas production routes. But it is possible. We have seen it, and we are looking into it, how to do it for biogenic feedstocks. And if we want to achieve higher conversions, then also the tail gas recycling has a huge potential. And yeah, these are the main challenges that we are now facing. At the end, I would like to invite you to the expert workshop that we are going to have at our syngas platform in Vienna in mid of March 2025. So there you will probably see our industrial, our gasification plant, and also Fischer-Tropsch synthesis plant. And this would be a really nice opportunity to have a more in-depth experience and knowledge about our processes. Thank you for your attention, and I'm happy to answer all your remaining questions in the chat or in the Q&A section.
Thank you very much, Theresa, for a very interesting presentation. And also for you, there is a couple of questions waiting in the chat already. So I think with this, we will open for the Q&A part of this session. I will still give you, Theresa, a bit of time to go through the questions that have come in and start with other panelists first, so you can check what you want to reply to in writing or orally. So bringing back all the presenters here into the center, I think this is a great asset that in a webinar like this, we have the experts here and we have a lot of knowledgeable people in the audience, so we get very interesting questions. The first question goes to Andrea Sonnleitner, and it is a tricky one. So what are the reasons for cancelled projects or for drawbacks in projects?
Yeah, this is quite a tough question. And I think there is no general answer to the question, because each project has its own reasons why there were setbacks or cancellations. And there are either technical difficulties occurring or non-technical difficulties. So one example is last year the Clariant plant in Romania closed its operation because they didn't achieve the targeted operational parameters. But a lot of the cancellations of announcements are dealing with problems in economics and also the political framework, so that the final investment decision didn't take place after the announcement. So it's not easy to answer, because it's from case to case different.
I agree, Andrea. Thank you for still trying to answer this question. And we realize that the projects fail at very different stages. So sometimes they are announced but never reach a final investment decision. And
Yes.
sometimes they are almost operational, but then the company runs out of money and it is still stopped, although almost there.
Exactly.
Thank you. So then the next question goes to Dimitris Kokoumpas. It is about costs for the pyrolysis and gasification based technologies. And I combine two questions here into one. At a unit cost comparison level, which technology is better, pyrolysis or gasification? And how feasible or how far away from market prices are the current productions anyway?
Thank you, Dina. Just to inform that the project is not, let's say, will not compare the two technologies. We see for both of the technologies, the opportunities and any constraints. Now, regarding the production of SAF and through these technologies, we have already done work in BioTheRoS Project with our BTG colleagues about the market dynamics and about the economic assessments. Just in brief, to inform you that always the biomass feedstock is a bottleneck. So this one is what we need to highlight and to try to overcome any difficulties, because always the feedstock, the biomass feedstock will increase, the cost and also the technologies. But take into consideration European allowances, especially for the airlines, then the cost can be comparable with conventional, let's say, fuels. Not exactly, of course, the same, but using this one, the European allowances, and this one can be comparable with fossil fuels. But always we have to take into consideration difficulties regarding the biomass supply chain. So this one is one of the critical issues regarding also that impacts also to the cost and of the biofuel.
Thank you, Dimitris. So then we turn over to Patrick Reimermann. The question here that is a recurring one is about the biojet production. So have you done a techno-economic assessment, like the costs? And have you thought about engaging in ESTM certification? And if so, are the aromatics a problem? So it's a combined question.
Wow. Yes. Let's take it on. Thank you for this question, first of all. Let's take it on one by one. About the techno-economic assessments, we are, of course, continuously making techno-economic assessments on our processes and of course also on the upgrading. What does it depend upon? One big cost for the process is of course that we need hydrogen, and this hydrogen needs to be sustainable. If we want to reduce the CO2 emissions, the specific CO2 emissions of a product with at least 65%, which is a requirement from the EU RED III, then we will need to use sustainable hydrogen, which is for a large part made from sustainable sources like solar and wind. And yeah, we very much hope that the price of this hydrogen can go down, but so far that is not really the case. And that means that hydrogen costs are still quite high, and they are quite a significant part of the costs of the our final products. If these costs are reasonable, then according to our calculations, our final product price will be comparable to other sustainable aviation fuel prices, which are currently in the market. So it very much depends on the hydrogen. Of course, the upgrading is also, the capex costs are also not that cheap, but the hydrogen is really the big part there. So that's the techno-economic assessment. Then about the ASTM. The ASTM, that is a requirement which you need to be able to use your fuel as sustainable aviation fuels. Well, people really don't like it when their planes don't fly but hit the ground. So there are very, very strict requirements, which everybody is thankful for if they fly. That means that there is a long process to certify your fuel. And we are at the moment at the stage where we are looking for a formal application. We are very happy that our biojet quite well conforms already to what is required for ASTM on their parameters. And we are looking at starting this process. We want to follow a good strategy so that we don't have to fulfill the full tier 1, 2, 3, 4 application process. If that works, and we think that we could certify this our process in about 3 years, which would be a best case. Did I get all the questions, Dina, or?
I think the aromatics content, do you see that as a hurdle?
The aromatics content is a bit higher, than some other fuels. For biojets, that can be, for SAF, that can be a problem if we use a very high blending percentage. It can also be an advantage if we can blend, for example, with SPK, sustainable aviation fuel, because there are hardly any aromatics. So it can be a problem, but it can also be an advantage.
Thank you.
Yeah.
Okay, yeah, then I will turn to Teresa Köffler. I'd like to combine two questions about the feedstock. So to what extent does the syngas composition depend on the biomass feedstock type, and in more general, how does the biomass feedstock affect the overall process? And a related question was just how do you secure continuous supply of feedstock into the gasifier?
Okay. So I'm trying to answer all these questions as good as I can, since my research focus is not the gasification part, but I still have some knowledge on that. So the feedstock quality and composition is really important for the syngas output. Since for example, if we use like wood chips, then the material is quite homogeneous, so we don't have that many, for example, sulfur components, or also we don't have that many phosphor contaminations. So if we then go to more difficult feedstocks, for example, to sewage sludge or forestry residues, we have way more heterogeneous components, or like also other heteroatoms like sulfuric components, and also nitrogen contaminations. And so the type of feedstock determines the syngas composition, and it is therefore quite difficult to like also operate the plant at the desired syngas composition. So we always have to adapt our process conditions to the feedstock. So, for example, in one case, we can tune up the steam ratio in the gasification part. Then we can try to adjust the temperature in the gasification reactor to obtain the syngas that we want. But the feedstock has a huge impact on that. And then the second question was again, what was it?
So how do you get the feedstock into the gasifier?
Yeah, so we have some screw conveyors, like some really big ones, and we convey them from the feedstock containers, and we bring them up via a chute into the reactor. So that is quite a simple process to do that.
Okay, thank you. So we just have a couple of more minutes. I have two more questions, one to Patrick and one to Teresa. Patrick, what would you see as the key bottleneck in upscaling of the pyrolysis technology? And Teresa, just to give you a heads up, just a comment on whether the Fischer-Tropsch SPK route at scale is too ambitious, fulcrum example. Just to give you a heads up. But first, Patrick, the key bottleneck in upscaling of pyrolysis.
Yeah, thank you, Dina. This is, of course, also a question which we ask ourselves and which we are confronted with. Of course, there are, for these technologies, upscaling, a difficulty is that, there is risks in upscaling and technological risks, and it's very difficult to find financing or to have others being able to share that risk. So that's always a very difficult thing. You have to do something new. You're not very sure if it works at this larger scale. For that, you need actually, a lot of process time to reduce these technical risks. Of course, there are also other issues. The certification is a bottleneck. I earlier told that in a best case that would take 3 years. And the renewable hydrogen, that's also a very big point. If we want to have a plant at the scales which I showed you, at 70 to 240,000 tons per year of HPO production, then you need quite a lot of hydrogen, and that needs to be made sustainable. It needs to be produced sustainable, and that's difficult. Of course, solar energy can operate and make a quarter of the time sustainable hydrogen, but then still 75% of the time it's not sustainable, or you have to have a very large wind farm. So we have some challenges. We remain, however, optimistic, and we think that this process is proven at a lab and pilot scale, and we think those scale-up issues are manageable with effort and time and work by a lot of people.
Thank you, Patrick, for sharing your insights here.
Okay.
And then, so for this very last question, there was a question, given that the Fulcrum facility has just recently failed. Do we think that Fischer-Tropsch SPK facilities at this large scale are probably too ambitious? And I realize it's a question that's beyond any of us, actually. It's a question that can be very much discussed, and people can share different views on this. But I still wonder, like, Teresa, what is your own take on this? Can we go up for very large scale Fischer-Tropsch facilities already, or would you rather suggest taking smaller steps? And maybe others that afterwards also want to comment on this. Teresa.
Yeah. So it is quite a challenging question, I would say. But I mean, there are already some large scale slurry bubble column reactor applications for the Fischer-Tropsch synthesis plants available. But the problem is with fossil based feedstocks. So the challenge that we face now is that we don't have these high this large amounts of feedstock, and therefore we have to downscale our reactors, which is which has a huge advantage, that we can have more facility, various amount, the facilities at different locations where we produce then the Fischer-Tropsch product at the site. But I would say we have to focus on developing the Fischer-Tropsch synthesis production route at a middle scale industrial range, I would say, because we have to look at our feedstock, and if we don't have these high numbers or high amounts of feedstocks available at once, then we need to use smaller scale reactors for these applications. And in my opinion, the reactor type that we're using would suit that purpose quite well, because it is quite straightforward in the construction of the reactor type itself, and it is quite flexible to operate as well. So in my opinion, we should focus on developing this technology at the mid-industrial size and not at the huge industrial size if we use renewable feedstocks.
Thank you, Teresa. Thank you. So I think we're well at the time to close for today. I think this is just the issue of about the advanced biofuels and scaling up these technologies. You need to take a risk. You need to try it out. There will be projects that fail. There will be others that go on. So I thought that was a very interesting question. So should we go for it or not? Yes, I think we should definitely go on with all our efforts to commercialize these technologies because they are very much needed for decarbonizing the transport sector. So with this, I would like to thank the presenters for your presentations and providing all the answers to these questions. I hope that we will still have access to the open questions later on, so maybe we can provide some more answers and put them on the website afterwards. I would like to invite everyone to revisit the website in a couple of days when the recording will be made available, and you can pick up presentations in PDFs, I guess, and maybe also some more answers to questions. Thank you for all the attendees here today. Thank you for joining us in this webinar. And there will be the next IEA Bioenergy webinar will focus on the valorization of plastic waste. So watch out for that one if you're interested. Thank you, everyone. Bye-bye.